Previously, we talked about problems with the stream ciphers. Those were encryption works one bit at a time. Changes in the plain text can show as a change in the ciphertext, and overall this can lead to some information leakage in certain situations, of course. So all in all, stream ciphers are not ideal. So is there an alternative? Yes, block ciphers are the next step in this. The idea is that we take an n-bit long block of plain text and produce exactly n bits long ciphertext block. For example, two of the more famous block ciphers are the Data Encryption Standard, or DES, and the Advanced Encryption Standard, or AES. There is also a three-layer successor to the DES called triple DES. The Advanced Encryption Standard is very ubiquitous. It has a block size of 128 bits, meaning that that is the minimum size of the encrypted data block. Any less than this will always come out as 128 bits with padding in the rest of the block. Consequently, the sizes of the output blocks are always divisible by 128 bits. The AES block size is fixed, but the key length can vary. So for example, you can use 128, 192 or 256-bit keys. And in fact, any key length that is divisible by 128 will also work. One thing to remember about block ciphers, and especially the keys used with block ciphers, is that the longer the key is, the slower the encryption or decryption processes are. Of course, the longer the key, the better the encryption will be. Block ciphers are built iteratively. That is, the cipher takes the key as a parameter, which is then expanded as a series of round keys, and the cipher algorithm encrypts the individual message blocks iteratively a number of times. A block cipher starts by taking the key, K, and expanding it to a series of round keys. The block cipher is an iterative process, meaning each block of data gets processed with several rounds using the different round keys. The number of iterations depends on the actual encryption algorithm, but for example, for AES, the number of rounds is 10. During each round, the block of data is processed using a round function, which uses the round key to cipher the data. So the algorithm in the round function is again the XOR operator. This is then repeated multiple times, in the case of AES, 10 times. The round functions are completely reversible, meaning that in order to decrypt the data, we just use the round keys in the reverse order. So a block cipher maps n bits of input into exactly n bits of resulting ciphertext. Block ciphers are built iteratively, and this iteration is based on two things. First, we have to define a key expansion algorithm, and then we have to define the round functions operation. Two examples of the block cipher are common, so there's DES, or the Data Encryption Standard, and AES, or the Advanced Encryption Standard. Let's look at the DES cipher as an example of how a block cipher works more in depth. So we use the DES as an example because it's slightly less complex in comparison to the AES. It's good to notice though that the DES standard on its own has not been secure for some years. So this is why in the previous we mentioned triple DES as an example of a block cipher. So triple DES is simply DES but encrypted 3 times over. So the operating principle of the DES is something called a Feistel network. Now what a Feistel network is a collection of functions, let's call them F, which simply map some binary input to a certain binary output. And what this mapping has to be, it has to be a reversible function, simply because we want to be able to reverse the process in order to eventually decrypt our data as well. So what a Feistel function normally is, it's a function that takes as a parameter some input string and produces a similar binary output string as well. The individual rounds within a Feistel net work somewhat like this. So to begin with, we have the input string, which is split into two. So one half of the input goes onto the right hand side of this Feistel net, and the other half goes onto this left hand side. And from here you can already see that there is some action going on. So the left hand side is easy. That is simply XORed with the result of what is coming from the right hand side, and then the result is then passed on to the next round, and it becomes the right hand side of the next round in this Feistel net. The right hand side, meanwhile, is first directly used as the left hand side of the input in the next round, and also it's given to this Feistel function here, which it was XORed earlier with the left hand side of this input. And then we simply repeat this process for some number of steps, depending on what our reversible function depends on. Anyway, this is the general idea of how a Feistel network consisting of Feistel functions would work. So the DES cipher is a 16-round Feistel network. And as we stated before, there is an input space of 64 bits, and then there is a 56-bit key. And like other block ciphers, this 56-bit key is expanded to a series of round keys, which are then used in conjunction with the 16-round Feistel network to produce our actual cipher function. So in this 16-round Feistel net, the individual Feistel functions work as parts of the cipher. So each Feistel function takes as a parameter one round key and a part of the, or some input X. As a result, there should be exactly 64 bits of output. And as stated before, because the Feistel network is supposed to be at least a collection of reversible functions, to decipher the messages, we just do this process but use keys in the reverse order. So let's dive in deeper to the Feistel function inside the DES. So how does this function work? Well, we take half a block of the input data that, as was shown in the previous example, and then we derive the round key, and in this case this round key or subkey is 48 bits long, and half of our individual input block of 64 bits is of course 32 bits, and these are XORed together, and then the result of the XOR function is fed onto a series of S boxes or substitution boxes. Finally, the output of these S boxes is fed into what is called a P box or a permutation box, which is not as important to understand the operation of the P box in comparison to the operation of the S boxes. What the P box here does, it simply shuffles some bits around for the output to be exactly 32 bits long. Remember, we're only ciphering half a block of input here. So everything in here is somewhat straightforward. Let's next look at what the S-boxes actually do. So the S-box, or a substitution box, is a very simple function. It's in fact a lookup table that one can find on Wikipedia. What it does is it takes 6 individual bits of input and maps it to 4 bits of output. For example, if our bit string was 0, 1, 1, 0, 1, 1. This would be 6 individual bits of input, and then we simply look up the resulting value in this lookup table. So first we need the outer bits, and in this bit string the outer bits are 0 and 1, so we are looking at this row. And then we look at the middle bits, which are 1, 1, 0, 1. So we are looking at this column. And as a result, we pick this particular substitution, and this will become the substitution or value of this S-box function. And as a result, we have established a fairly simple workflow. So it begins by doing the key expansion, so using the cipher key to derive a set of round keys. Then these round keys are used in conjunction with these Feistel functions, and this Feistel function basically consists of an XOR function and an S-box substitution. And the S-box substitution is simply a lookup table function which maps a 6-bit input into a 4-bit output.